me briefly summarize what we did last time. Last time I explained to you the Lieb-Thirring inequality as an inequality for orthonormal functions, as a generalization of the Sobolev inequality. And then I explained to you that Lieb and Thirring were interested in this because of stability of matter, which was what they could prove with physically relevant constants. And then I switched to this formulation about eigenvalues of Schrödinger operators and explaining you that there's an equivalence between the Sobolev type inequalities and the eigenvalue type inequalities. Okay, that was roughly speaking what we did last time. We talked also about optimal constants. The program for today is I wanna follow that Lieb-Thirring paper from 1976 and extend that inequality about eigenvalues for a whole range of parameters. Okay, this is a form of the Lieb-Thirring inequality as perhaps some of you have mostly seen, and it's certainly one of the very famous versions of that inequality. And again, I will talk about constants and so on. And then in the second part, I will explain you some more about this equivalent formulation, how to use orthonormality. And then I'll talk a little bit about partial overlay. That's roughly speaking the outline for today. Okay, so we will start with Thirring inequalities. For eigenvalues of Schrödinger operators. I will again keep the proofs to a minimum today. There will be proofs in this course, I mean don't worry about that, but I'll do those afterwards. I just want to explain the picture for you. I mean I want to explain to you what are the important questions, because in some sense this is more important than some of the proofs that you can do. If you're already interested in looking at some of these things, if you feel uncomfortable with this, me just telling you stories, let me give you a couple of references. So there is one thing, there's a survey that I wrote a couple of years ago, the LT inequalities, recent results. And open problems. And you find that on the archive. And then the other one, if you really want to know more, there's a book that we wrote together with Henri Poincaré and Timo Weidel. I mean, that's very thick, but it's perhaps not the best place to start on. Please start if you want to, but that has all the details in there. And we will come back to these points next time. But let me talk now about these Lieb-Thirring inequalities for Schrödinger operators, which is actually the version that's mostly focused on it. So here's the reminder, we work on RD. There's a function v on RD, and concerning the negative part, we assume that this belongs to LP, and there will be certain restrictions on the power, and I hope these restrictions become clear in a moment. And there are essentially no restrictions on the positive part. I mean, in most of the inequalities, you just want to look at negative potentials. I mean, so that, it's the negative part of the potential that wants the electrons or the particles to bind. And the positive part for many of these things you can ignore. But sometimes in the arguments, it's good to know that you can have whichever positive part. Okay? All right, and then what I said last time, then you can define minus Laplacian plus b, defined via quadratic forms. Say it again. I will prove this or talk about this next time, but let's just believe that we have this. If v is bounded, say, then much of this is easier. Define our quadratic forms as self-adjoint, adjoint, no semi-bounded, operator in L2 form. And if P is smaller than infinity, so if you are in an LP space, this means, so the negative part should go to 0 at infinity. Okay, in some average sense. If P, then the negative spectrum is discrete. By this I mean, it consists of eigenvalues of finite multiplicity that can accumulate at 0 only. Eigenvalues En. And then let me state now the theorem. So let gamma be greater or equal than 1/2 if d is equal to 1. Gamma greater than 0 if d is equal to 2. And gamma greater or equal than 0 if d is greater than 3. Then there exists a constant L gamma d such that for all v as over there, the sum of these eigenvalues, see, compared to last time, remember last time we took just the sum of the absolute values of the eigenvalues. Now what I'm doing this time, I'm raising them to a certain power. All right? And the power, which powers I'm allowed to take depends on the dimension. Gamma equal to 1, that's the old problem we had last time, that's allowed in any dimension. But if you go to smaller and smaller powers of gamma, then you need to be careful, and that only works, I mean, you need the dimension to be sufficiently large. And we'll see why. This has a very simple explanation. Okay? And then this is smaller than this quantity Vx minus gamma plus d over 2 Vx. And so the point, notice the order of the quantifiers, there exists a gamma such that for all v. So the constant is independent of v. It does depend on gamma and v, however. Alright, so that is the Lieb-Thirring inequality for eigenvalues. Now let me make a couple of remarks. The first remark is there's a gamma equal to 0 is allowed in dimension 3 and higher. What does it mean? Well, just whenever you have an eigenvalue, you count 1. So in other words, gamma equal to 0 means that you have a bound on the number of negative eigenvalues. For gamma equal to 0, sum n, n to the 0 is equal to the number of negative eigenvalues. And remember, we agreed that eigenvalues are counted according to multiplicities. All right. So that's, of course, a very important special case. We discussed, I mean, the original version for stability of matter was gamma equal to 1, the sum of eigenvalues, but naturally the number of negative eigenvalues is also an important quantity that you need in these applications. Okay, let me give you some references. For this theorem, so the non-endpoint cases, you see that in some dimensions, all dimensions except dimension 2, you have an equality. And as is often the case when you deal with inequalities, the endpoints are the hardest ones, because there you somehow don't have any wiggle room. Okay? And so if we are away from endpoints, then this is what Lieb and Thirring proved in their original paper. Then, let's talk about the endpoint cases. There's the endpoint case gamma equal to 0. If d is greater or equal than 3, this is called the CLR bound. And these names, CLR, stand for Zwickel. So it's a little hard, you know, I'm going to write down years, but these are, I mean, this is a paper, this is an announcement, but as Barry Simon tells, he received the proofs within the same week in his mailbox. So they were both, Zwickel and Lieb were both in Princeton, they sent him their results, and they came up with it essentially at the same time. And then there's the R, which stands for Rosenblum. He was not in Princeton, he was in Russia, and he actually had the result back in 1972. That's the year of the announcement. But the year, I mean, a Russian announcement in a small journal, but the time it was published in the West was, I think, also 1976, the full paper with the proofs. Anyway, so people agreed to call this the CLR inequality, because these are completely different methods. They're all important, and each one of these methods has been generalized to other settings. So I think it's important to study all of them and also to recognize their contributions. When you're interested in the values of constants, then Lieb's bound is still the best one. I mean, this is, in 3 dimensions, I should say. You know, this is almost 50 years old, but nobody has been able to improve that. People have been able to improve it in dimension 5 and higher, I think. But dimension 3 is ways. There were later yet alternative proofs by Conlon, Pfefferman had a proof. So we'll talk about these proofs later on in this course. I will probably give you the proof of Rosenblum, which explains some of the techniques, and in particular the connection with Sobolev inequalities rather nicely. And I'm doing this also because there is one more remaining case, this endpoint case, gamma equal to 1/2 in 1 dimension, and that was solved much later by Timo Weidel in 1996. Using a method that perhaps in retrospect is similar to this Rosenblum method, and actually if you combine these two things, then you can get a proof for everything. All right. Now, of course, when I was calling this the endpoint, what I was saying implicitly is the inequality cannot hold beyond that range. Okay, so if you go in dimension 1 below 1/2, or if you look at gamma equal to 0 in dimension 2, that cannot be true. Okay, so range, and we'll see that in a second. Range of gammas is what? So for instance, in 2 dimensions, you cannot bound the number of negative eigenvalues just in terms of the integral of it, in terms of the L1. That doesn't work. And L1, you see, the meaning of this 1/2 in 1 dimension is that you do have an L1. That it's a number of, the sum of the square roots is bounded by the integral, and so L1 is in a natural sense an endpoint space, and it's interesting to compare that. In some sense you have the bound with L1, in other cases you don't. Anyway, This is the theorem. Let me now talk about a special case, or a consequence actually of this theorem, which is an independent question. I call it the one particle constant. Oh, let me perhaps add one more thing here before I do this. It's also, there is a dual version for gamma greater than 1. You know, what do I mean by this? We started with the Sobolev inequality for orthonormal functions, and we argued that it was equivalent to this term for gamma equal to 1. So now you see this, and you ask yourself, well, for other gammas, can I turn this into a Sobolev inequality? And the answer is yes, when gamma is bigger than 1. That was shown in a paper that's not particularly well known by Lyons, Pierre and Paul. Oops, I have the year there. Here.
1993 probably.
Yes, perfect, thank you. All right. But I should, add the caveat that so far this duality people have not been able to really use it. It's a bit strange. I will tell you some arguments about constants, what they knows, and so on. They have, obviously, since they're completely equivalent again in the sense that there's a Sobolev type inequality which has a constant that is in one-to-one correspondence with that one. All these theorems should have analogs in that setting, but they are easier to prove in one. This is to say that really you have two pictures, but you have to choose the right setting to prove something. Or perhaps it's worth to better understand that. When you go below gamma equal to 1, what's special about gamma equal to 1? That's where convexity breaks down, right? This thing is a convex function of the eigenvalues whenever gamma is greater or equal than 1. So this duality is sort of a convexity argument, and it is sort of that convexity that you need. I don't know of any good version, even if there's not an equivalence, a complete equivalence, I don't know what to do for gamma less than 1. So that's also something perhaps worth looking at. We don't see the gamma equal to 1 really as a big threshold in many of the questions. So there's something to be understood there. Anyway, so right, now I wanted to talk about the one particle constant. And so this starts with a question that was posed by Keller back in 1961. Okay, so that was quite a while ago. And so what Keller asked is, among all potentials V with given LP norm, which ones minimize the ground state energy, so the smallest eigenvalue of minus Laplacian. Okay, it's sort of a question of isoperimetric flavor. Right? You ask, among all, curves of a given length, which one maximizes the enclosed area. That's a classical isoparametric problem that we know. And there are higher dimensional versions. Now here, what you're fixing is sort of the size of the potential. You measure it in some LP, where P is sort of up to you to choose. It's a question for every P. And now you look at the eigenvalue, want to make that as small as possible. Okay? And so I should say Keller's paper is not rigorous. So he poses the question, and then he goes on and does some things, and then he arrives at an equation and then draws some conclusions or something. Now, it's of course an achievement that he asked that question. Now, the point is that you can formulate this. This is sort of equivalent to find best constant and optimizers, find optimizers, I should say, optimizers in the inequality E1 to the gamma is less or equal L gamma D1 or D of x gamma plus D over 2 dx. So I've written the inequality in that Lieb-Thirring language. Let's see, where does this equivalence come from? Right? So when I say I fix the norm, so an LP norm, obviously the P is equal to gamma plus D over 2. That's here, that's the equivalence, obviously. And so that's just a rewriting or reparametrization, and nothing happened there. Now, the other thing is it's obvious when you look at an LP norm, you have to pay both for the positive part and for the negative part. And since you want to make the eigenvalue small, you just kill the positive part, or if you want to flip it down, then it becomes negative. Okay, so therefore here we don't see an LP norm really, but we just see the integral of the negative part. Okay, so that also should not concern. Now the next thing is, here it's if there is a given LP norm, that's just a scaling argument. So if for a given LP norm you can ask that for the LP norm to be 1, or put differently, you can write an inequality less or equal than such an thing. Okay, that is just because you can scale. If you scale the potential, then you can give that LP norm an arbitrary value, and well, the eigenvalue will change accordingly. Right? Okay, just by unitarily changing the space. Okay, scratching coordinates. All right. So good. So that's the inequality, and finding optimal potentials. V means finding optimal potentials. Good. Yes, please.
Could you recall what so you've got L gamma D, and what is the one?
That's sort of by definition the optimal constant here.
So sorry, my question was, what is the difference between this one, which has a 1 as a superscript, and the one on the...
Correct, yes. So this one is an inequality that holds for all eigenvalues.
Oh, okay.
Okay, so here, I mean, it's a good point that you're making. I mean, why did I write it as the inequality? Well, because if you have the Lieb-Thirring inequality, then of course if you can control everybody, you can control the lowest one as well. Okay, so Lieb-Thirring certainly implies that. But potentially, this one holds with a better constant than that.
Right.
Okay, and so therefore I use that notation with a 1 as optimal, by definition, optimal constant. So when you talk about optimization problems, I mean here for instance this isoparametric inequality, I ask for the optimal potential, but really before I should ask is what is the optimal way, I mean the optimal constant that I have. And then I ask in the second round, I can ask, is this attained? Is there an optimal shape?
Can you recall the scaling for the Schrödinger?
Yes, absolutely. So if I take psi t of x is defined as psi of, say, x over t, t to the minus t over 2. That is an L2 preserving scaling. Then I have minus Laplacian plus v psi t equal to, and so now I differentiate here, I get a t to the minus 2 out. Okay, now I have a minus, yes, this, let me do it like this. I write t to the minus d over 2 minus t to the minus 2 Laplacian psi evaluated at x over t. And then I say, because this comes out, so this is plus v of, so let me write it as this in a silly way, psi, so I want to write it at x over t. Right? But now, because I'm evaluating this product at x over t, it's a t dot. All right? So, in other words, what I've shown you is that minus, here for instance, minus Laplacian plus v is unitarily equivalent to minus t to the minus 2 delta plus v of t dot. All right. So if I can even rewrite it differently. So let me put the t to the minus 2 out, and then I have a t squared v of dot over t. Okay. So that is the scaling that I make. So that if this has an eigenvalue, what should I say? So using this scaling, you can adjust the norms that you have, except for one special case, gamma equal to 0. So let me comment on that later. Okay, but in general, for typical gammas, you can adjust the LP norm as you want, but what you will get is a fact that the eigenvalue scales out. And in this way, you can arrive at such an inequality where the eigenvalues control that potential. Okay, good. Any other questions? Okay, good. So that's what we have there. This argument, by the way, that's thanks for pointing this out. I mean, this is the same argument shows you that if you insist to have a gamma here, then that power has to be gamma plus d over 2. Okay, that just by scale invariance. Just like in the Sobolev inequality, you know there is, if you don't have an L2 term, there's only one exponent that works potentially. And similarly, if you insist on that, you can only have that. Okay? Good. Now, right. So the meaning of this inequality, remember we were talking here, what does it mean, gamma equal to 0? So meaning for gamma equal to 0, it means that if the integral, that's the interpretation of Keller's problem for gamma equal to 0, if the d over 2 norm is small enough, then no negative eigenvalue. Okay, so that's I mean, it's sort of in the spirit, of course, of this theorem up there, but it's a little bit different. Okay, let me, since we're there, let me prove this assertion for you, because that's the easiest one. And then we'll see how we upgrade things. And I should say that, so what follows is the argument of Lieb-Thirring. So Lieb and Thirring discussed this in their 1976 paper. And so they I think were not aware of Keller's problem, but they gave a rigorous discussion of this problem and a rigorous solution. Okay. And what they found is, in particular, connection with Sobolev inequalities. And that's very easy here. So, proof. So think Sobolev. And now by Sobolev, I mean really the critical Sobolev. So the exponent is 2d over d minus 2. The dimension is strictly greater than 2. And SD for me is the sharp constant. So what do I do? So I look at the quadratic form of my Schrödinger operator. Here it is. And the only thing I do is I apply Hölder's inequality to the potential. Okay, so this is greater or equal, this is Hölder, minus, so the positive part of V I throw away, and then I have the negative part, and I'll do it with d over 2, and look and watch, what is the Hölder dual? Well, we know that out there we gotta have a 2d over d, because the exponents have to sum to 1. And then in there we had a 2, and then we have to multiply by the inverse of that, so that gives a 2d over d minus 2dx. And now this thing here is exactly the thing that appears in the Sobolev inequality. So therefore, this is Sobolev, gives me integral radical squared dx minus, so this is 1 over s t integral v of x minus d over 2 dx, 2 over d, rd, integral gradient u squared dx. You agree? That was Sobolev. But now, see, it's the same gradient here and there with power 1, so the only thing you do is you factor this common term out. And then you see, so if the integral of v of x minus d over 2 dx is smaller, actually equal smaller or equal than sd to the power d over 2, then the quadratic form of the Schrödinger operator is greater or equal than 0, and so therefore we cannot have a negative eigenvalue. And now you can play the game backwards. What do I mean by this? By this I mean that if backwards. So what I've shown you is that the optimal constant, so by definition, this is the optimal constant for non-existence. Okay, so then we've seen that the optimal constant for non-existence is smaller or equal than the Sobolev inequality, the Sobolev constant to the power d/2. That's what we've shown, right? Because we've seen that this condition in terms of the Sobolev, did I make, I guess I made a minus. I've shown you that the Sobolev constant gives you a necessary condition. Now I'm going to show you the opposite. So I'm going to show you that you have equality. Okay, play backwards. So if integral v x minus d/2 less than 1/L 0 d1 means that this thing here is greater or equal than 0 for every u. So what I'm going to do, I'm taking v equal to a constant, say lambda, times u to the, what is it, let me just say 2d/d-2, minus 2. Why am I choosing this? Well, I'm choosing it so that what I get here is exactly the Sobolev term. So what do I learn? So I learn that gradient u squared is dx is greater or equal lambda times u to the 2d/d-2 dx, provided what? This thing here, lambda to the d/2 times integral, so I'm just plugging this in, there's a computation that you can do, so this is u to the 4/d-2, plug it in there, and so you see this is u to the 2d/d-2, our dx is less than 1/L 0d. So now let's take lambda defined by that equation. It is strictly less, but then you can pass to the limit. So take lambda going from below, if you want, to 1/L 0d1, integral u to the 2d/d-2 dx. Whole thing, that's also divided. L 0d1 to the minus 2/d. Yes, and then you plug this in, and then you learn the gradient of u squared dx is greater or equal, so I plug this in, L 0d1 to the minus 2d. Right, that's what we did there. And then you have the integral of u to the 2d/d-2 to the 1 minus 2/d. And look what that is. That is the Sobolev constant. That's the Sobolev inequality. And so if SD is the optimal constant in the Sobolev inequality, well, the optimal constant has to be at least greater than the constant we get, minus 2/d, and that's the reverse inequality that we have here. So summary, L0D1 is equal SD to the minus D/2. And that, I mean, you need to think this is 1976. That's the year where Aubin and Talenti proved the sharp, found the sharp constant in Sobolev inequality. That was very much in the spirit of the time. You have now a problem that it connects to the Sobolev inequality. I mean, the whole Lieb-Thirring family sort of generalizes this Sobolev inequality. You can interpret the Sobolev inequality as a criterion for non-existence of negative eigenvalues. Okay. Yeah.
Can you just explain it again why the fact that there is no eigenvalue implies an up or down on the best constant?
By definition, we said L0D is the largest constant, the smallest constant such that this assertion holds. It's the smallest constant, this thing is the smallest constant such that this bound on the potential implies no negative eigenvalue.
Okay, so maybe what was the same as before?
Yes, I mean, it's exactly this. It's exactly this. I'm just doing the special case here for gamma equal to 0. Right? I mean, I just wanted to do that case first because I think it's a little easier to understand.
Okay, so it's not a priori the same constant for gamma strictly.
Exactly. For gamma strictly positive, we don't, I mean, I will tell you in a second. But I just wanted to talk about that. But you know, see, now you can, I'm jumping a little bit ahead, but there was this Lieb-Thirring conjecture. Remember we talked about last time, where it was conjectured that in small dimension, the constant that you have for one function should be the good constant for all functions. Now, I mean, in the spirit that was actually in the paper, you might wonder, is the constant in this inequality, the constant in the bound of the number of negative eigenvalues, is that the same as the Sobolev constant in small dimensions? It's not true in dimension 7 and higher, but in dimension 3, 4, 5, I think, 6, I'm not quite sure, it's still open. Okay, and so that is, I think it's a very nice problem. It has all the, you know, conformal invariants. I mean, people love the Sobolev inequality, for instance, because it has this geometric meaning and this conformal invariance with different reparametrization. The CLR problem that I described to you, finding the best constant in this inequality for gamma equal to 0, has exactly the same invariances. So is it that this potential, which is the best, the largest potential, potential that saturates this inequality, is it also the potential that saturates the inequality for more than one eigenvalue? Okay? It's an idea of this repulsion phenomenon of eigenvalues. It's sort of the potential wants to split into different parts, this geometric phenomenon of bubbling, and each one piece has just one eigenvalue, which is supposed to happen in small dimensions. Okay, good. So that was that argument. That was a little proof. Now I want to do the same thing for gamma positive. So argument gamma positive. And so what I need is, I need Sobolev interpolation inequalities. Here we go. Oh, sorry. Before I do that, I think you see already something now. Look at this example. We know that this Sobolev inequality fails in 2 dimensions. Right? Because that would give us L infinity, but we don't have a boundedness in L infinity. So you just play the same thing, just the fact that this Sobolev inequality is 0, and so that tells you that this constant L is infinity. It's really the same argument. In the argument, we never used the fact that the constant was finite. So I mean, just so this constraint here, if you had even the simpler inequality, let me write it down. Even, so same argument, gives L0, 2, 1 equal to infinity. By this I mean that short for there is no finite constant such as it was. Okay? Since no solar into and I told you that this range of gamma was optimal in the Lieb-Thirring theorem. Now I told you that even for the Keller problem, this range was optimal. Okay, good. Anyway, let's move on to gamma positive. This inequality needed dimension to be 3 and higher, but we do have Sobolev type inequalities in lower dimensions. The only thing is we need to have some additional support from an L2 term. So here's the inequality that I'm referring to. So I want to control a Q norm in dimension D by a geometric mean of the gradient and the L2 norm. L2 norm of the gradient and the L2 norm of the function. See, often people write the Sobolev inequality as a gradient u squared plus u squared. Now that's dimensionally a bit shaky, because a gradient, you take a derivative that scales differently. So when you care about these things, we like to do it in this, write it in this way, as where you have some geometric mean between these two things, because then dimensionally it makes sense, and mathematically you can go from one to the other, just by scaling. The same scaling argument that we did over there on the board, just scale, the two terms scale differently, so you have the Sobolev inequality in the additive version, you get it in the small additive version. And that's really the better way to look at it, at least in this. Okay? Good. So what do we have here? So there's a range of Q's. Q equal to 2 is boring, but so I'm always assuming Q greater than 2. In 1 and 2 dimensions, you can go up to infinity, infinity included in 1D, excluded in 2D, and then in higher dimensions, well, we have this endpoint that we've seen before. Okay, so this, I'm assuming that you know this. The Sobolev inequality. Okay, and there is this other parameter theta that appears, and this parameter theta is uniquely determined by scaling. What do I mean by this? Well, I mean, I'm doing this argument, what was it? That you kindly pointed out, so you replace the function by its dilate, do the computations, things scale with different powers of t, and there will be a theta, and this gives you a relation of theta. And so what is it? So here there is a dx that counts as d-dimensional, the gradient cuts off 2 lengths, so it's d minus 2 times theta plus, here we just have d times 1 minus theta equal to, so what do we have here? We have d times 2 over q. So that's the scaling relation that determines theta once you have q given. Okay. Now let me see whether I can squeeze in the theorem. No, I don't think I can. So the thing that I will tell you is that the one particle Lieb-Thirring constant, this L gamma D1, is equivalent to this constant S in the Sobolev interpolation. Okay, so theorem, again, this is this Lieb-Thirring 1976. So assume 1 over gamma plus d over 2 plus 1 over q over 2q. Use now q over 2, no, q over 2, that's right, is equal to 1. Where does that come from? A relation. I mean, if I tell you where this relation comes from, then I tell you the proof of the theorem, before I even have written down what the theorem is. The point is, you have v minus u squared. Remember, that is what we have up here, where we apply Hölder's inequality. I want to use Hölder, and now I want to put q into LQ. And then I want to put v in this gamma plus d over 2 space. And since u to the q, 2 over q, and I want to have this inequality valid, and so I need this relation. And so now what you should check is that as gamma ranges over this parameter regime, q ranges over that parameter regime. That's the key thing there to note in this Lieb-Thirring. At the range where you have Sobolev inequalities valid, that's that box up there, corresponds to the range where you have Lieb-Thirring valid using this duality relation. All right, so now that was, I told you the proof before I told you the theorem, so let me write the short constants. L gamma d1 and S, how did I write it, dq? Are related L gamma d1 times S dq to the 2 over d over 2 theta equal to d times q minus 2 over 2 to the d over 2. I mean, don't worry about it. The precise meaning, I want you to get the gist of it, not the precise numbers. It's analogous to what we had for the Sobolev inequality last time, for the Lieb-Thirring for gamma equal to 1. This is the corresponding statement for the one part of the problem in now for general. And there is more. I mean, not only are the constants related, but remember Keller was really asking about the optimal potentials. And so now, similarly, optimal potentials for the one particle Lieb-Thirring thing are related to optimizers in the Sobolev inequality. Okay. Moreover, optimal potentials V star and optimizers U star are related, and let me say Sobolev integration optimizers are related by V star of x to the gamma plus d over 2 minus 1 is equal to constant star of x. And so the proof of the second part is, again, I mean, this is the proof of the theorem, right, this Hölder inequality, and you just check when you have equality in Hölder's inequality. And equality in Hölder's inequality you have if, I mean, this is equal, I mean, if this is equal to that, or this equal to that. Okay? And you have one more invariance, sort of the Sobolev interpolation inequality you can multiply by constants. So therefore I have one more invariance there, so I'm not completely precise. Okay, so that was the Lieb-Thirring proof of this, or the Lieb-Thirring solution of this Keller problem. I write here proof. I will not go through the details, but I think you have them all on the board, right? I mean, there's the gradient, you here, you make Hölder's inequality, now you get two terms, and now you have a gradient to power 1, and here you have a gradient to a smaller power. And then you optimize over what it is. And then you arrive at such an inequality. If you have questions, we can go through it afterwards, but roughly speaking, the idea is the same.
Please do V star square, yes. V star together.
Okay, I trust you. I mean, right, it's this, yeah, right, this it is. It's, I mean, this, you have to set this term equal to that. Okay. So now, instead of proving this, let me talk about the consequences it has. Consequence number one, in dimension 1, in 1D, the constants S1Q and the optimizers corresponding misers are known explicitly. Okay. I mean, one-dimension things become simpler because the Euler-Lagrange equation becomes autonomous ODEs, and those you can solve. And actually, this was done by Nage already in 1941. Just, I mean, finding the sharp constant. And what is perhaps interesting is that this corresponds to V star of x equal to a certain constant that depends on gamma divided by cosh squared of x. Don't make a mistake here. I should double check that statement. But I mean, so either it's a cos squared of x or it's a power thereof. But I think it's always a potential one time. Okay, and yeah, these are the optimal potentials. And remember, the Lieb-Thirring conjecture says that that the constant that works for one eigenvalue works for all. So these are the profiles that you want to have. It's the one eigenvalue, and when you have several eigenvalues, you just take copies of the one over cos squared very far apart from each other. Okay, good. All right. That was first consequence. Now, in d greater or equal than 2, we don't know these things explicitly. I mean, and gamma strictly positive. Gamma equal to 0, we know that's the Sobolev optimizers, we know that explicitly. Okay. But if as gamma is positive, one can show spherical symmetry and uniqueness. So up to translations and dilations. Of optimal potentials. I mean, that's actually quite heavy. You really have to sit there and work. But what helps you is that you have this reformulation of Sobolev optimizers. Because they're Sobolev optimizers, they satisfy an Euler-Lagrange equation, positive solutions to that, and then you can start playing games using elliptic. Okay? But it's by no means easy. But at least we can say that this scalar problem that I raised has a unique solution. There is a certain shape. Good. And so you can compute these constants to arbitrary accuracy by numerical means. This is important for certain applications. Anyway, what else did I want to say? Perhaps I should comment on it. Let me just say it in words. You know, when d is equal to 1 and gamma is equal to 1/2. That was when we had the L1 norm. Then in Hölder's inequality we have an L infinity on the other side. So everything needs to be understood in the right way. Right? I mean, it's morally still the same result. The potential then happens to be a delta potential instead of that one. But you can get this. Okay, and for the sake of completeness, let me sketch Keller's argument, just so that which gives, I mean, so far this was Hölder's inequality that everything was based on. Now let me sketch how Keller arrived at that conclusion. So there is Keller's argument. So Keller says that he assumes that there is an optimizer. He doesn't bother about existence of optimizers or so. But then he says, let's perturb the optimal potential. Okay? And then we know by that something called the Feynman-Hellman formula. That's a formula, or I mean, that's the physicist's name. Mathematicians, I don't know, call it Rayleigh-Kato perturbation theory, that says how the eigenvalue of a Schrödinger operator changes when you change the potential. Okay? And the change in eigenvalue is that. Okay, so that's the inner product. So psi star is the eigenvalue, So let me write it down. Minus Laplacian plus, this is the optimal potential, psi star is equal to E star psi star. That's the eigenvalue equation satisfied by the optimals. Now I changed the potential slightly, so W is an infinitesimal perturbation of V. Okay? Now, how does the norm, my constraint, change? Well, that we know, that's just the derivative of the LP norm, right? So then, by the Lagrange multiplier rule, we get that this is, so it's minus E star to the gamma plus E over 2 minus 1 times W. That holds for every W. And I'm equating that, that's the gradient of the eigenvalue, differentiated with respect to the potential. That's the gradient of the constraint. So they have to be equal, so that means psi star squared is equal to lambda V star to the gamma plus D over 2 minus 1. And see, that is exactly, actually I forgot the absolute values here, that's exactly this equation. Okay, and so from there, Keller went on and just plugged it in, and the minus Laplacian minus, so what is it, lambda to some power, psi star, this minus Laplacian psi star, minus lambda to some power. Now I have to solve it, there's a certain power here, psi star equal to E star psi star. So you arrive at a nonlinear equation for this psi star. Right, I'm just plugging in this expression, I'm solving this for V, plugging it in this equation, and I get a nonlinear equation for the psi star. And then Keller goes on and studies this equation. So Keller never talks about Sobolev inequalities, but Lieb-Thirring observed that sort of using the Sobolev inequality, you can make this rigorous, and then a posteriori, for the optimizers of the Sobolev inequality, you get that equation. Okay? That's the relation of the two things. But, you know, I mean, at the end, when I want to prove properties of the optimal potential, when I want to find that it's radially symmetric, when I want to show that it's unique, then I do have to go to this equation that Keller suggested earlier. Okay? That's, but I mean, just so that the two things are really related and you can go from that. Okay, good. Now, I still want to do some things. This was the one particle constant. We call it one particle constant. So, I mean, it's about one eigenvalue. But sort of when you have this in mind, this picture of orthonormal functions, then we only have one function, and so on, which describes one particle. So therefore, typically people call it the one particle constant. Okay, that's the terminology. We've learned now one particle constant is the same as the constant in a Sobolev interpolation. What I want to talk about now is the semi-classical constant. That's the constant sort of when you have many eigenvalues. So from now on, it will be very useful to write, to abbreviate this sum as that. I'm taking the operator, I'm taking its negative part, I'm raising that to the power gamma, then I take the trace. If you have had a course in spectral theory, you know there is a spectral calculus and you can do exactly that. But otherwise you can just think of it as an abbreviation for that. But I think it's very suggestive. So I want to use it, and then as we go along, when we really talk about operator theory, we will justify it. Okay, so now what I want to do is, I want to look at the case where I have a large constant in front of the potential. Potential is fixed, I have a large constant in front. Now the homogeneity, I take out the lambda. Lambda is larger than 1. Take it out, and what I get is a small constant in front of the Laplacian, which, as we know, is the regime where we can apply the semi-classical approximation. So this is equal. What does the semi-classical approximation tell us? Well, it tells us that we should look at the symbol of the operator. Obviously, the symbol of the Laplacian is just psi squared. I must not forget that there's a 1 of lambda. Then the potential is already diagonal. So this is what we're taking. Now if I take a function of that operator, I take the same function of the symbol. It's a function on phase space. And then instead of taking the trace, I'm integrating over phase space. With respect to x and psi, and with a normalization constant 2 pi. And then I do the computation that I alluded to last week, that this is L, so that's an equality. A certain constant is lambda v of x, negative part to the gamma plus d over 2 dx, with L gamma d semi-classical equal to psi squared minus 1, negative part to the gamma d psi divided by 2 pi to d. That's a computation. I mean, go sit down and do it. It's a scale, right? Just for every fix x, and then change variables in psi, and then this is what you get. And so the point is, again, that this trace, this is what we have on the left side of Lieb-Thirring, and this is what we get out on the right side of Lieb-Thirring. They're the same, except that we have here now a constant which may or may not be the same as the one that Lieb-Thirring gives you. So we'll talk about, so this is called while asymptotics. It is valid. It can be shown to be valid if and only if LT holds. What I mean by this is, we can always prove these asymptotics when V is nice. Say, I don't know, compactly supported and continuous is probably. Okay, then we have it. But is it true, or while asymptotics true, whenever the right side is finite? That's a question. And the answer is, if you have a Lieb-Thirring inequality, yes, then it is valid. That you can prove using the Lieb-Thirring theorem, as I described last time. But interestingly, if you cannot prove Lieb-Thirring, if Lieb-Thirring fails, meaning gamma being strictly less than 1/2 in 1 dimension or gamma equal to 0 in 2 dimensions, then there are potentials for which the right side is finite, makes perfectly sense, but the left side does not converge to the right side. Okay? So this is sort of non-trivial, and this shows you really the tight connection between asymptotic statement and Lieb-Thirring. I mean, that Lieb-Thirring really captures a lot of effects, even from a semi-classical point of view, which is somewhat different from all the things that we've described so far. I think this is what we're going to do next time. So next time, this is the time when we talk about proofs, and I will tell you about this semi-classics. Right? I mean, how does one actually prove this? There will be some nice arguments, I hope. Anyway, so a generalized Lieb-Thirring conjecture so we know that the optimal constant is at least as big as the one particle constant and as the semi-classical constant. But that's clear because, I mean, the constant that I need to bound one eigenvalue, if I want to bound more eigenvalue, I need to have at least a constant that's so large. And if I have these asymptotics, then the bound cannot be true with a smaller constant. Okay, so this is what we have. Now, at gamma equal to 1, which we discussed last time, the conjecture of Lieb-Thirring was that we have equality here. And that is this big, famous Lieb-Thirring conjecture that, well, everybody would like to solve. There was the question, is this a more general phenomenon? Does one have a similar conjecture? I mean, does one have equality for any gamma? And I have to disappoint you, this is in general not true. Lieb-Thirring were first perhaps a little bit over-optimistic, thought it might be true, but this has turned out to not always be true. However, in a large regime, parameter regime, one that we still don't understand completely, it is true. Okay, and so in particular, so this may, equality may or may not hold depending on gamma n. So the conjectured equality is conjectured for gamma equal to 1, any d, and d equal to 1, any gamma. There are results about the second thing that I will tell in a minute. There are regimes where we know that this inequality is strict, and there we do not have at the moment a counter conjecture. So all the works throughout the years that have disproved the conjecture really didn't come up with anything else. With Mathieu Levine and David Gontier, we've thought about this. We have a couple of pictures, and I mean, this is something that we might discuss more later on. But let me now state a very nice argument of Eisenman and Lieb. And then I give you a theorem, and then we'll have a break. The Eisenman-Lieb argument. That's the following theorem, a lemma, or whatever you call it, due to Eisenman and Lieb. From I think the late 70s, 78, and this says gamma maps to L gamma D divided by L gamma D semi-classical is non-increasing. So this makes an assertion about the unknown Lieb-Thirring constant. And the most important thing it says is that if at some point you know that this constant is 1, so imagine you've been able to prove the Lieb-Thirring inequality with the y constant, the constant from these asymptotics. Then, for every larger gamma, you also have the same statement with the constant y asymptotics. Okay, so in particular, if L gamma D is L gamma naught, let me write L gamma naught is equal L gamma naught D semi-classical, then L gamma D is equal L gamma D semi-classical for every gamma greater or equal than gamma naught. And the proof is super simple and super nice. Let me show you. We use the following thing. Let's say, so take, what do I have? Gamma greater than sigma, sigma small. This is an inequality about numbers. E minus gamma, that's the object that appears in the Lieb-Thirring inequality, right? It's the eigenvalue, the negative part. We only look at negative eigenvalues, so therefore I'm writing E minus, and then we raise them to the power gamma. Okay, and now there's a representation. I can write this as an integral over E minus T minus the sigma, and I guess that's plus, sorry about that. There's plus, and then, right, and then there is a t to the gamma minus sigma minus 1 dt, and then there's a constant that I don't care about. C is equal to C sigma. Gamma, the only thing I care that it's a positive constant. That's clear, right? That's just by scaling. I mean, you just put in E equal to minus 1. E equal to minus 1 gives you a value for that constant. And then for everything else, you get it by scaling. Okay, right? Because, I mean, there's the sigma and the minus sigma and the dt and the minus 1. So what's left over is the gamma, which is the same on both sides, just by homogeneity. So why is this useful? Well, let's look at our Lieb-Thirring trace. This is now equal to, see, this is a bunch of eigenvalues. It's a sum of eigenvalues. For each eigenvalue, I use this identity. And then I interchange the summation with the integral in the representation. So that is 0 to infinity, trace minus Laplacian plus v plus t minus sigma t to the gamma minus sigma minus 1 dt. You agree? So I get the representation of the Lieb-Thirring sum for gamma in terms of Lieb-Thirring sums for smaller powers, but with a potential that's shifted. All right? Now, what does Lieb-Thirring say? Lieb-Thirring says that this is less or equal than something, but I want to write the something in a clever way. And what I want to do is, I want to write it as, you know, the semi-classical symbol. I want to write that as xi squared plus v of x plus t negative power to the sigma dx dxi divided by 2 pi to the d. That's not quite right, because, I mean, according to this computation, you have to divide through by L sigma d semi-classical. And instead you have to put the real constant, the one that you actually have. Am I making sense? I mean, I could have written just this thing times the integral of v. But then I'm undoing it in order that I get the symbol out. And the price I have to pay is I have to divide through by the semi-classical constant. Now, why does this help me? Well, because now, see what I did here is I interchanged the trace, or the summation of the eigenvalues, with the superposition parameter t. Now, I'm interchanging back, I'm interchanging the double integral over phase space back with the superposition integral. And what do I get? I get, well, the c times the superposition integral with this measure. But that gives me back exactly what I want. Sigma d L sigma d semi-classics. I'm just copying this. Now this gives me the integral of xi squared plus v of x negative part to the gamma. Is everybody following? Just doing it backwards. Now, I'm doing once again the computation. The computation says that this is equal to L sigma d semi-classical, L gamma d semi-classical, integral v negative part gamma plus d over 2 dx. I've done once again this computation that I mentioned, right? That you can, that in this semi-classical integral, you can perform the xi integration. And when you do this, you get out this constant. So what I've shown you is that if you have Lieb-Thirring at the smaller value at sigma, then you get Lieb-Thirring at any larger value gamma with that constant. So I've shown you that the optimal Lieb-Thirring, you know, I mean, this may or may not be the optimal Lieb-Thirring constant. The optimal constant is certainly smaller than whatever I found. So that is L sigma d divided by L sigma d semi-classical times L sigma gamma d semi-classical. That's what we've shown, and we've shown that for every sigma smaller than gamma, and that's exactly the monotonicity. That's the Eisenman-Lieb argument. Yes, please.
Yeah, you are using for your argument the semi-classical result. right?
No, no, I'm not. No, I'm just using the computation. This is just a purely mathematical trick. The mathematical trick is that I write integral v gamma plus d over 2 dx equal to L gamma d semi-classical is equal to that thing. That's everything I'm using, and I do not use semi-classical analysis. Okay? I mean, of course, the inspiration comes from semi-classical analysis, and we'll discuss sort of the connection to semi-classical analysis later. But here it was just a computational tool. You know, I mean, you can play the same game in terms of gamma functions. I mean, I could have written here a gamma function. Right? I mean, you write this out there. There's spherical coordinates, the angles give you the measure of the sphere, which you can express in terms of gamma functions, and then there's a beta function left over, which you can express in terms of gamma function. So there's a whole bunch of gamma functions hiding. Then you write this. I mean, you can write C in terms of gamma functions, but even if you don't do this, then there will be gamma functions here and gamma functions there. Right? If you do this argument, and at the end you use some formulas about gamma functions which allow you to transfer that back. But the way I wrote it is, I think, explains a little bit better, to me at least, what's really going on. That really this is an argument that is in the spirit of semi-classics. That Lieb-Thirring is really bounding the true quantum quantity by the semi-classical approximation, perhaps with the wrong constant. And this is the quotient by sort of how much Lieb-Thirring is wrong. Wrong in the sense wrong compared to semi-classical. Okay? And what this says is that if gamma is larger, the larger gamma gets, the closer we get to semi-classics. Let me just, before the last thing that I want to write down on the board, is there's one more theorem that I want to mention, which is related to that, and that is going to appear in these lectures. This is a theorem, so that appears, I mean, I'll tell you a little bit about the history later, but let me just write Lieb-Thirring in d equal to 1, and then Lieb-Thirring and Weidel. And that theorem says that L gamma d is equal to L gamma d semi-classical for all d greater equal than 1 and for all gamma greater equal than 3. Okay? So in dimension 1, we have the Lieb-Thirring inequality with the constant given by semi-classical analysis, and that was already observed by Lieb and Thirring in dimension 1 for gamma equal to 3/2. Then Lieb and Eisenman pushed it to all gamma greater or equal than 3/2 in one dimension. And then, so this was 1976. And then Lieb-Thirring and Weidel, in a paper from 2000, were able to extend this result to any dimension, still having this constraint gamma greater or equal than 3/2 from this original Lieb-Thirring work. And I should say in one dimension, the 3/2 is optimal. In one dimension, you cannot have the inequality below gamma equal to 3/2. That's part of this conjecture that I was mentioning, the equalities conjecture in dimension 1 for any gamma. This result settles this conjecture for greater than 3/2, and according to the conjecture, you would have the one particle constant for gamma less than 3/2. And so I think this gives credence to this conjecture. There's another result that Hundertmark, Lieb, and Thomas proved that again gives credence to this conjecture, we talk about that. And then there was this result from last week, remember, by Chicour, Densler, Jean, and Trélat, who proved something again in the spirit. So, I mean, all this adds up confidence that in dimension 1 the Lieb-Thirring conjecture should hold. We do not know why in higher dimensions, dimension 3 and higher, the semi-classical constant should be valid already down to gamma equal to 1. That's sort of completely open. But at least I think this gives you some idea of that there is evidence for this conjecture. And I guess now we have a break, and I think I can introduce a special guest that we have. It's not Lieb-Thirring, but Elliot Lieb here, who is in Paris at the moment from Princeton. And so if you want to ask some questions in the coffee break, say hello. I'm glad that you came. Thank you very much. All right, we assume in 15 minutes. All right, can we continue? Good. So I want to give you now an overview. I want to step back a little bit and talk about topics on Lieb-Thirring inequalities. So, I mean, one question is, what are the sharp constants? We've seen this question come up now a couple of times. It's certainly one of the most important questions, but on the other hand, I guess we cannot all spend all our time just trying to improve constants. So what I want to tell you is, what do we people working on Lieb-Thirring inequalities, what do we do the rest of the day? And we don't work on sharp constants, okay? So this is a short list of topics which just should show you that these things that we've seen so far are just a small fraction, but that these phenomena that are captured by Lieb-Thirring inequalities are actually more general. Okay? So, one thing is Lieb-Thirring inequalities for, let me call it Schrödinger-like operators. And so perhaps the simplest example is if you just raise the Laplacian to the power s. So, you know, when s is 1, then this is the old thing. When s is 2, 3, 4, when this is an integer, then this is a differential operator of higher order. Now, coming from applications in physics, even fractional powers of s, fractional values of s, have been considered. This was already in the 80s, long before these fractional Laplacians became fashionable. Okay, and so inequalities for this operator have been studied. Okay, and so what happens is that, remember there was this array of conditions on gamma. If gamma is bigger than that in this dimension, if gamma is bigger than that in that dimension, and so on. So I think these things become even a little bit more clear when you look at them for general S. Okay, because then you see what they're related to, validity of Sobolev inequalities, some endpoint cases, and so on, and you can better distinguish the cases. Okay, so this case is rather close to the cases that we had. This is essentially all solved, except constants are essentially not known. For any, there is no parameter of S for which there are somehow competitive values of constants. Okay, now the next thing is, again, this comes from motivations in physics. So what I'm doing is, let me write it like this. So think S equal to 1/2. So that's the square root of the Laplacian plus a positive constant, and if you want, you can normalize the symbols so that it's 0 at the origin. Okay, That's what you need when you try, in a caricature fashion, take relativistic effects into account in quantum mechanics. All right, so S equal to 1/2, dimension is equal to 3. That's really important for these applications, and people have studied, in particular, stability of matter for this operator. That was open for quite some time, and then it was settled essentially by Lieb and Yao in '87. And one part, just like we had stability of matter for before, Lieb-Thirring inequalities play a big role. Now, why is this case harder? See, in stability of matter, your potential is 1/x, and 1/x, that's like 1/length, and the square root of the Laplacian, that's also 1/length. So the two things now compete against each other. And you're really not allowed to lose anything. I mean, there will be a critical constant, and if you want to get there, you have to be very careful. Okay, so that was the motivation of studying this. Now, even let me just forget about stability of matter. Just look at this from the Sobolev inequality point of view. We've seen that Lieb-Thirring is closely related to Sobolev inequalities. Right? Now, what is a Sobolev inequality for such an operator? You see, this operator, when m is a constant, think m equal to 1. When the Laplacian wins, for functions that are at high frequencies, this is essentially minus Laplacian to the s, like in the line above. But when for low frequencies, when the Laplacian is small, you do a Taylor expansion, and then this is like Laplacian. Okay, so what is the critical exponent for the Sobolev inequality? Okay, and so somehow you get in this realm of Orlich spaces, right? So it's no longer that you estimate a function to a power, not u to the, remember before we had 2d over d minus 2, but we have to estimate a different power for large values and another power for small values. Okay, and right, because sort of when functions are large, that's where the gradient is large, so this corresponds to high frequencies. So large values of the functions correspond to square root of the Laplacian, small values of the function, then we have the Laplacian, then we have the ordinary function. Okay, so you have these Lieb-Thirring inequalities, but they're more complicated because it's not just rho to a power, or functions to a power, but really some Orlich type norm that takes different behaviors into account. So that, again, has been understood long time ago. Dobishi in 1983, I think, did some work about this, which then was useful for stability of matter and other things. Now, yet another thing what we study sometimes. Let me go back to the Laplacian, even though you can ask the same thing. So you think your potential consists of two pieces. One is a fixed background, and one is sort of the small guy that sits on top of it. And you want to bound inequalities just in terms of the small piece. And this one is either an explicit guy or belongs to a certain class of functions. So for instance, what one can do is one can take v0 of x equal to minus d minus 2 squared over 4x squared, and that you might recognize as, that's called the Hardy potential. And so this is such a Lieb-Thirring inequality in terms of v. We call those Hardy Lieb-Thirring inequalities. One can prove them. The conditionals gamma change, but they're useful, or more precisely, if you do them with the S version. That's why I do the S version. Do the S version here, and then it's again, because then you have the Coulomb potential, and then it's relevant for that. Okay, so this is, but you can also look at periodic V if you want, periodic V naught. And so what can you say then? So there are many questions of understanding this. I don't think this is completely safe. Yet another thing which is important in physics is if you add a magnetic field. Okay, so A is a vector potential. So RD valued function RD. And we'll look at operators of this structure. And your goal is to prove a Lieb-Thirring inequality that does not depend on the A. Again, if we're just doing very naively the semi-classical approximation, then we have xi plus A of x, right? That's the thing that we've been doing before. I know. I told you a couple of times now already, do the xi integral for fixed x. But see, for given x, when you do the xi integral, you can just shift it, and so there's no A. So the semi-classical approximation, at least if you do it naively as that, does not have an A. So Lieb-Thirring inequalities actually hold, that can be proved, with a constant that's independent of A. Question that has been around for a long time, that nobody has been able to answer, is the optimal constant with A the same as the optimal constant without A? So sort of in all cases where we do know the optimal constants, and in all cases, all proofs with non-optimal constants, they give the same with A as without. But there's no general theorem that you cannot use the A to sort of lower the energy. Okay, so that is one of the important questions here. Another question, so if we go to 3 dimensions, there's something like the Pauli operator. This is now an operator acting on C2 valued functions, no longer scalar functions. There are things called the Pauli matrices, and if you don't like that, let me just write it in that way, because I'm not sure whether it's plus or minus sigma dot curl of A plus. Okay, so what you get is you get sort of a background potential, a little bit like what I said up there. Okay, and you want to prove bounds just in terms of V without using that background potential. And but this background potential is very critical, and it can produce, this operator can have 0 eigenvalues. And this makes the life quite a bit more complicated. You cannot, even though, you know, I told you the semi-classical approximation does not see the A, but here in this problem, you do see, I mean, the inequality cannot hold with an A independent constant. But really capturing the dependence on A or on the curl of A is really a complicated problem that has not been solved yet. Even, you know, not talking about sharp constants, just, you know, how do the inequalities look like, what does one need? Okay, so this is a sample of questions about Lieb-Thirring inequalities that are currently investigated. Okay, now let me talk about something else. So this is still rather close to Schrödinger operators, right? I mean, there's some variations, looks a little bit different, but it's still the same whole. Let me ask you a completely different question, which still, I mean, is connected with Lieb-Thirring inequalities. So LT, how did I call it here? Or let me just call it inequalities for orthonormal functions. This goes now further back to what we did in the first lecture. Remember, I told you Lieb-Thirring was a Sobolev inequality where we have a constant that's independent of the number of functions, the functions being orthonormal. Let me put this very general. Okay. So here, let me start. I have a Hilbert space, so it's very abstract. I'll start with let H be a Hilbert space. Let X be a measure space. Okay, and let T be an operator Hilbert space into some LQ space. This Q is some number. I want to have a Q bigger than 2. I don't want the other space to be a Hilbert space as well. And Q needs to be bigger than 2. And I want to assume that this is a bounded operator. So what does that mean? That means that if I apply the operator, let me write it like this. X is the measure on X, okay? Then this thing is controlled by psi to the Q. It's inequality. Now, what would be the Lieb-Thirring version of such an inequality? That's the question. Does there exist a power sigma which should be smaller than Q over 2? Such that, so what do I want to do? I want to take orthonormal functions, psi n, apply the operator to it, take the square, take the sum, I take n such functions now, and then I raise it to the power q over 2. See, I want you to compare it to the thing we did up there. dx, integrate over x, and I want to control this by n to the sigma. If the inner product between these functions is delta and m, meaning they're normalized and they're orthogonal to each other. That's a question, right? I mean, by no means am I saying that this holds, but I'm raising the question, or this is a meta question. Any operator t that you find, you can ask this question. And I'm trying to explain to you that's a meaningful question. Let me first tell you, where does this constraint come from? Okay, so the thing is, so trivial with sigma equal q over 2, even without orthogonality. Where does that come from? Well, you have t psi n squared to q over 2 dx. 2 over q, now you apply the triangle, right, in LQ over 2. Alright, you apply the triangle inequality, and so then you get the sum over n, get the sum out. Let's remember that it goes from 1 to n, and then we have the norm of each individual squared, that's the individual guy, to the power q over 2, to the 2 over q. Okay, and so what is this? The functions are all normalized, so this is less or equal than 1. Because for a single function we have the inequality, so this side is less or equal than n. And so if you put the power q over 2 to the other side, then you get the required inequality with sigma q over 2. We did not use orthonormality. Now the question is, if we do have orthonormality, can we beat the triangle inequality? But that is the thing that we learned from Lieb-Thirring. Lieb-Thirring said that, I mean, if I take all the psi in Lieb-Thirring the same, then in the Lieb-Thirring inequality the constant goes to 0, but if we have orthonormality in Lieb-Thirring, the constant has to be 1. The constant has to be, I mean, of order 1, independent of the number of particles. That's sort of a translation of that question. It's a question for all these operators. Now let me mention the prototypical result, which is, for example, let's So that's due to Lieb in 1983. And so the operator that we take is the operator, sometimes called fractional integration. Or hardy little bit Sobolev inequality, or weak-young, many names for the same thing. So what does that inequality tell us? Well, the inequality tells us that if let me write it for one function first, if I take the convolution and I raise it to the power, and again there is, everything just follows by scaling, d minus 2 alpha dx, then this is smaller than psi in L2 to this power 2d over d minus 2 alpha. Okay, so you are in RD, and alpha, I mean, it has to be so that you can divide. So alpha is between 0 and root. The weak-Young inequality. If you ordinary Young would say that if you convolve an L2 function with a function in some LP space, you're in another LP space. But here, you can even convolve with a function that logarithmically fails to be in the LP space, is in this weak LP space. Okay, so that's the inequality we have. We know that. And so Lieb has actually computed the optimal constant in that inequality. But that's not what we're interested in. Same here, actually. But that's not what we're interested in here right now. But we're interested in that this inequality has this Lieb-Thirring type phenomenon. Namely, if I take now a whole bunch of functions, I convolve all of them. Okay, I take it to the power d over d minus 2 alpha dx. Then this can be controlled by n if we have orthonormality. And you see, I mean, just what we have to beat that that was the question, whether we can beat the triangle inequality exponent. So here the sigma is equal to 1, and the exponent from the triangle inequality, that's this exponent, and obviously this exponent is bigger than 1, so we actually have beaten the triangle inequality. And this exponent that one gets here, that is actually optimal. Okay? So that is one of these things, and actually one can show, so this is equivalent, this is in a certain sense equivalent to the CLR inequality. Not as strongly equivalent as when I'm usually using the words equivalence, that we have exact constants, but I mean, in a sense, it can be quantified. Okay, but what I'm trying to say is, so this is a question about Schrödinger operators, bounding the number of eigenvalues in terms of integral of the potentials, which you can phrase in terms of such inequalities and the behavior on a number of functions. Okay? So convolution with a power function is an operator T that satisfies this thing. And now there are a couple of other examples that I want to mention. And essentially the question there is whether one can understand this, whether if I give you an operator and you look at it, whether you can tell me that it has this Lieb-Thirring phenomenon, and if so, with which exponent. What is the exponent sigma that you get here? That's a question that we cannot answer at the moment. So here's another example. So that's much later. This was jointly done with Mathieu Levine, Elliot Lieb, and Robert Saringer, back in 2013, and then together with Julien Sabin, we continued working on it and pushed things a little bit. So what did we do there? We looked at the Strichhertz inequality. What is the Strichhertz inequality? You have a function psi on Rd. You evolve it by the free Schrödinger equation. And you know, so in L2, the norm is the L2 norm is conserved along this flow, but really what you want to quantify is the dispersive behavior of this evolution, meaning the solutions should sort of, disappear, become smaller and smaller, disperse. Okay? And one way of quantifying this is by using these Strichhertz inequalities, where you take now, you go away from L2 norms. And so the way we set it up, we call this exponent 2q. It's not the usual notation. So I'm just recording what the Strichhertz inequality is, okay? So this is p over q. And so you integrate over space and you integrate over time, and this integral is finite and controlled by psi and p. You should think of this, and this means sort of that the solution goes to 0 as time goes to infinity, just because there's an integral over time that's finite. Okay, and again, there is some scaling relation between the powers that are involved. This is the L2 norm. The scaling relation between the powers is 2p plus d over q equal to dimension. And then there's a relation for q. This is not the maximal range that you have for a single function, but it's where we can prove aversion to orthonormal functions. Okay, so same story, I think by now you know it. Take the square sum of these objects, raise them to the power q, so that it coincides with the thing above. An outside power dt, and of course what's important is the power of the number function that's involved. And you get a power, I don't remember it by heart, but it is the optimal power. We can prove that this does not hold with a better power than that. And number two, I mean, this is a power that beats the triangle inequality. So the Strichhertz inequality has this Lieb-Thirring phenomenon. That orthonormality helps decreasing the dependence on the number of functions. And once again, this inequality is useful in questions from mathematical physics. So you can, for instance, look at dynamics of large systems of fermionic particles, and you essentially think that you have infinitely many particles, I mean, properly interpreted, and then you need to get the right power out. Because if you don't have the right power, then everything is lost. And so in these applications, it's really crucial that you get this power. Okay? And so this has been done by Mathieu Levine and Julien Sabin. And let me mention one more result of that flavor. This is from the same paper with Julien Sabin. This is the so-called Stein-Thomas inequality. we're now going in the direction of harmonic analysis, right? So we started sort of with Sobolev inequalities, which is more or less like calculus of variations. Then we moved to this fractional integration, sort of in between. There were Stricherts, and now if you view Stricherts from the point of harmonic analysis, that is a Fourier restriction theorem. And that, the classical version of that is the Stein-Thomas inequality, and let me tell you what that is. I skip the intermediate step and I immediately go to the orthonormal version, because now I guess you know what will be the thing. So we're living now on the sphere. Our functions live on the sphere. And we compute their Fourier transform. Just pretending like the functions are measures on the sphere, and we compute the Fourier transform of these measures. All right, okay, good. We take the square sum, and then we take a certain power, which is d plus 1 over d minus 1, and you integrate this over all of Rd. And so it's a little bit surprising that you have a function on the sphere, which you Fourier extend, and then it belongs to LP on the whole space. But that is actually true, and that's the optimal power even for the single function, and that's what Stein-Thomas proved in the 70s. And then we can prove this inequality d over d minus 1. Once again, this power is the best power that you have. You beat the triangle inequality, and you cannot beat it by more than that. Once again, this inequality has applications. I mean, it's fun to prove these things and to study it from a purely mathematical point of view. I mean, you take your favorite inequality that you find somewhere, and you ask yourself, does it have a Lieb-Thirring version? But I mean, for these inequalities, it's even more fun if you can use it afterwards for something. And so we could use them to prove bounds, number one, on eigenvalues of Schrödinger operators with complex potentials. See, when you have complex potentials, potential in absolute value goes to 0, but it's complex. And so the bad thing is these eigenvalues could accumulate at positive energies. And that, if you think about how the resolvent blows up at a positive energy, you see that this operator is sort of the leading singularity. And so if you can control this, then you get sort of Lieb-Thirring-like bounds for eigenvalues. Okay, of Schrödinger operators with complex potentials. And if that is not justification enough, there is something in harmonic analysis called the Kakeya problem that's of course quite difficult and complicated problem. In 3 dimensions, there was a solution announced just last week or 2 weeks ago. With this bound, you can get a bound on the dimension. You cannot prove the conjecture. We're far away from proving. I mean, I don't want to give you any wrong ideas here. But still, you get some results if the dimension is greater than d plus 1 over 2. Which is, I mean, if you do it by hand, you really you need to work. I mean, people have done better since then, definitely. But you see, I mean, I found it quite surprising that using this Lieb-Thirring technology, you can say something about that problem. And of course, it motivates us to improve this and sort of getting better Lieb-Thirring inequalities to get closer to these things. Okay, so these were some sample results about this, what we call Lieb-Thirring phenomenon, and I mean, you see it's not complete. I mean, this is really done by case-by-case study. I mean, somebody gives me this operator, and then you sit down and work hard and you prove that. And then somebody gives you that, and you sit down and work hard and you get that inequality. But we're sort of lacking, I think it's fair to say, we're lacking a general understanding of what is really going on. And so I think that beyond, these concrete Lieb-Thirring inequalities, I think that's an interesting phenomenon that deserves to be studied. Okay? There was a little excursion just to give you some ideas. I doubt, honestly, that we will talk a lot about it in this course more, but if you have questions, feel free to ask me. Let's see. So, what we're doing next, that's a completely different thing now. I want to talk about Laplacians on domains. And I want to talk about inequalities for Laplacians on sets. Okay. And there are some conjectures about these which are related to the Lieb-Thirring conjectures, which actually predate the Lieb-Thirring conjectures and which are also open, but where there are some nice results, and I will tell you a little bit about those. Once again, most things will be without proofs, but those will be supplied later. I'm trying to paint the global picture. Okay. So what we have is, we have an open set omega. Right now we're not assuming anything about its size or boundary. Okay. And then I want to define directly a normal Laplacian we denote them by minus Laplacian. I put the omega downstairs and the D for Dirichlet or the N for Neumann upstairs as self-adjoint operator, self-adjoint non-negative operators in L2 of omega by the quadratic forms. So what do we have? Just the Dirichlet integral, gradient u integrated over omega with form domains H10 in the Dirichlet case and H1 omega respectively. Okay, so that's the Sobolev space of order 1. This consists of functions in L2 whose distributional gradient belongs to L2. And if I put the 0, then I mean the closure of functions whose support is a compact subset of omega with respect to that. Okay, good. So again, there's a theorem in the background that you have, if you have a quadratic form which satisfies this and that properties, then there's a self-adjoint operator to it. Again, these are things that we talk when we are in the next few weeks. But that for the moment, let's assume we have this, and then we have eigenvalues. Okay, so if, before I talk about that, let me emphasize that the definition of these operators does not assume any regularity on the set. Now, if omega is nice, the boundary of omega is nice, then functions in the operator domain minus delta omega Dirichlet and minus normal respective satisfied and functions u satisfy u equal to 0 on the omega for u d nu, that's a normal, equal to 0 on the omega respective. That explains the name, right? So people historically have called this the Dirichlet boundary condition, this is the Neumann boundary condition, and you can check that if things are nice, then these operators that we defined in such an abstract way actually reduce to these classical operators. But, I mean, here you need at least Lipschitz, or I mean, that's wrong, but it's hard to prove that without being Lipschitz. Or here you need a C11 for the boundary, and so in general we don't have it, but we also don't need it. But it just explains you the names. I wanted to say that. And so we think of this as sort of a relaxation of the operator with such boundary conditions, and that as a relaxation of the operator with those boundary conditions. Okay, just so that you know where the names come from. Okay, good. And now, let me see the point that where we started was always the semi-classics. I mean, we did the semi-classics in our first lecture, we did it earlier today, so let's do it once again here. Assume omega is finite measure. And if, and in the Neumann case, the extension property. What does that mean? That means there's an operator defined on H1 omega that goes to H1 of RD, and that is the identity of on omega. And of course the operator should be null. Okay? It's an implicit definition. But you can check, for instance, that sets with Lipschitz boundary have an extension property. So rather weak property. Okay. Then the spectrum of these two operators, of the spectra of, and you know, I'm using this hash sign if I'm referring to either Dirichlet or non-Neumann. So discrete, and satisfy. So let me call n lambda minus the Prussian omega is equal to, I'm going to write it that way, L 0D semi-classical, that's our friend from earlier today, right, the constant that I wrote there, times lambda to the d over 2 times relatively small the remainder as lambda to infinity. And I should tell you what that means. That is the number n of lambda of this A is equal to the number of eigenvalues, of course, counting multiplicities, of minus the Prussian omega hash less than lambda. And according to the notation that we've been using earlier today, I will write it in this Lieb-Thirring fashion with the 0 upsteps. It's a little artificial right now, but you'll see in a second why it's useful. Okay. So these are asymptotics. Those go back. This goes back to while a long, long time ago, 1911. And this this is also the reason why these asymptotics for Schrödinger operators are called Weil asymptotics sometimes. Okay? Because it's the same basic philosophy that's going on. People have studied this a lot over the years. There's a famous paper by Mark Katz where he was studying this from, in terms of heat kernels. And then Biermann and Solomjak were emphasizing to really push the regularity assumptions to as low as one can. In particular, I mean, in the Dirichlet case, you have this optimal result that as soon as the asymptotic coefficient is finite, you have the asymptotics. That is due to Rosenblum, the same Rosenblum we've seen before. A couple of years earlier, he was a student of Solomjak. And the other thing I should say is that in the Neumann case, you need something extra. I'm not saying that extension property is the weakest you can do, but there are bounded connected sets where the Neumann Laplacian has non-discrete spectrum. Okay, where you have even continuous, even absolutely continuous spectrum if you want. Okay, so there this fails badly. So in the Neumann case, you need something about the boundary. And what you choose depends a little bit on what you like and the techniques you want to use. But since we have Sobolev spaces floating around anyway, and the whole lecture is related to the Sobolev type inequalities, I think this extension property is a natural assumption. Anyway, okay, so that's that. Now, I'm writing this in terms of the number. That sounds a little bit strange, doesn't it? So let's turn it into the eigenvalues themselves. Say lambda n are the eigenvalues. You can rephrase the whole thing. You just divide through by this. So the nth eigenvalue is n divided by L0d semi-classical omega to the 2 over d times 1 plus L over 1 as n goes to infinity. That's the way, like, probably Weil has thought about the inequality. You have the nth eigenvalue is n to some power. One remark before I go on. What's remarkable about the asymptotics is that it's independent of the boundary condition, right? I mean, I can take either the Dirichlet or the Neumann eigenvalue. The leading term in the asymptotics only sees the volume. That's a certain universality. Now, why am I writing it if this is the intuitively understandable way of what the asymptotics says, why am I writing it in this complicated form? I'm writing it because this expresses the locality, really, of the asymptotics. Let's see that the number is sort of proportional to the volume. And that's how the proof really goes, because you sort of cut the domain into pieces, and that corresponds to cutting the domain into pieces. So that's really, when you really want to prove the inequality, that's somehow how you prove it. And you see it even clearer afterwards. So this implies for every gamma positive that the corresponding Lieb-Thirring traces obey a similar law. So that's an exercise with numbers. I don't, I'm neither proving that these asymptotics are equivalent to those asymptotics, nor am I proving that these asymptotics imply those asymptotics, or actually are equivalent. This is really easy. But that theorem itself is not easy, and that we will talk about next time. Anyway, I guess you see already where this is going. We have asymptotics. Next thing will be inequalities and constants in the inequalities, right? Okay. So, and that was actually done, as I said, before the work of Lieb-Thirring. But it's nice to see this connection. So let me say that we are interested in the short constants trace minus Lopatian. We talk about Dirichlet first. And we put a D upstairs, right? So we have the L gamma D's with lots of superscripts up there. But so that's the D for Dirichlet. Turing Dirichlet constant. What's the best constant? And now, the other inequality. It's perhaps a little bit surprising when you see it for the first time, but perhaps I can convince you of that. I'm doing the same thing, I'm just writing Neumann. Neumann has the same asymptotic, first term in the asymptotics, but actually you can check that if you look at the subleading term in the asymptotics, it actually has the opposite sign. So while in the Dirichlet case, the subleading term is in favor of this, in the Neumann case it says that this cannot hold. But what can hold? Well, the reverse inequality. L gamma D Neumann omega L to gamma constant. And I can write here these such constants exists in the sense of a finite and L gamma D Neumann is positive. That can be shown. So it's not very hard. Now, the conjecture, which goes back to Columbia, says, I'm looking for the year, 1954. Conjecture says that the constants should be the semi-classical constant Okay, so for Lieb-Thirring, we think that the semi-classical constant should only set in when gamma is large enough, but Polya suggested that this is true in this setting of the domains for any positive gamma. And so for every d greater than 2, and here I can remark d equal to 1 is easy. Because you can reduce yourself easily to the case of an interval, and for an interval you know the eigenvalues, and then you can find that it's true. Okay, so that is Polya's conjecture. And so the relation to the Lieb-Thirring conjecture is heuristically minus Laplacian omega directly is minus Laplacian plus v, where the potential is equal to 0 if x is in omega and plus infinity if x is outside. And so I guess really, if I put here minus lambda, which is the thing that appears in all these inequalities, then we take this as the potential as p minus lambda. And then, so then you plug this potential in and you compute the Lieb-Thirring integrals, and then you arrive at exactly these points. So that's, for instance, one way of proving that the constants exist, at least when you have Lieb-Thirring constants. Okay? Now, just like the Lieb-Thirring conjecture, the Polias conjecture is very wide open. There is one result here that I want to mention. And so that was by Filanov, Levitin, Poltarovich, and Chaire, and it's proved in 2023 in Invenciones, and the second part is in preparation. And you know, the amazing thing is this year, and what this says is if omega in Rd is a whole, then it's true. Okay, so I mean, one had to wait for 50 years in order to prove it for the ball. You know, for the ball, the eigenvalues are explicit, but you know, what does explicit mean? They're zeros of Bessel functions. And they're ordered, I mean, they're coming, it's a mess because different angular momentum channels are mixed. And so, well, okay, so you can order them as far as you want. And then you can say, okay, perhaps somebody did the semiclassics on the other end. And so then there's the gap between where semiclassics kicks in and where up to which point you can order them with a computer. And sort of these are serious people, but the numerics just weren't enough to close that gap. Okay, so even this proof is partially numerically, partially computer assisted. They estimate the error terms. I mean, it's correct, at least, yeah. They pay attention to rounding errors that you get there, but it's not by no means an easy proof or something. Right? And that's even for the ball. So that was open until not so long ago. So the Dirichlet case is what's published, and I think Neumann in 2 dimensions is published. But Neumann in higher dimensions they announced in several conference talks, and I think it's sort of the point is to really get the numerics completely verified. But that's really where we stand. I mean, this is quite far away. I should say one more thing here, perhaps. I should have said it over there already, but remark. We can use the same Eisenman-Lieb argument. Eisenman-Lieb. If one of these constants, I mean, here's the semi-classical one, then it's always going to be semi-classical afterwards. Because if you remember, what did Eisenman and Lieb do? They had this superposition formula where you added a constant t to the potential. But you know, you have the inequality for all lambdas, so if you have lambda plus t, you're still in this class that Eisenman and Lieb had, so therefore the very same argument gives you this. And so therefore, if these guys were able to prove it for gamma equal to 0, then we get it for all positive gammas as well. But of course only for the ball. So before we finish today, I want to mention two results here. I had intended to give the proofs of these two things. This would have been the things that I wanted to prove. It's really beautiful proofs. But I have to wait another time. So here's a theorem that's due to Polya. You know, he conjectured this in 1954, and I think he proved this in 1961. And his proof about in the Neumann case was not as perfect as it could have been, so that's what was proved in 1966. So that says if omega is tiling, then we have the and then again the Eisenman will happen everywhere. What does tiling mean? Tiling means that omega is tiling if there exists a sequence of orthogonal matrices and of a sequence of translation vectors such that the rotated and translated sets, which I denote by omega j, satisfy omega j intersected omega I has measure 0. So they're disjoint, the sets, and they cover everything. Let me give you an example. Every triangle is tiling, because what do you do? So here you have your triangle. Right? Now you make a copy of the triangle. Oops. Draw here. You take another copy. I hope I'm making sense, right? So you just take it and I mean mirror it over here, and then you translate of the original one, and so you can tile a whole strip, and then you can, I don't know, just translate this like something. So this in particular also says that parallelograms are tiling, regular hexagons are tiling, and you know, you can look at these pictures by Escher, where they have tiling domains that are not only triangles. Okay? So this is a certain class of sets, but it's certainly not a generic set. But anyway, so there's a proof that if your set omega has this property, then the conjecture works. It's a beautiful proof, as I said. It really just uses the semi-classical asymptotics, the Weyl asymptotics that we've been talking about. But I want to finish on time. So the second theorem, positive theorem that I want to mention it's due to Berezin in 72. And then rediscovered independently by Li and Yao, it's Peter Li and S.T. Yao, geometers, that in 1983 a very nice paper about the circle of ideas. In particular, Li and Yao give an independent proof of the CLR inequality. Remember, we had the CLR, the 3, then we had this Pfefferman proof, the Conlon proof. Li and Yao also gave a proof of this. Okay, so, and besides that, they prove in this paper the following thing, and then there's a work by Kröger, Karl Kröger, from 1992, and that says if gamma is greater or equal than 1, then L gamma D Dirichlet is equal, L gamma D Neumann is equal to L gamma D semiclassical. Okay, so there we do have when gamma is large enough, we do have the semiclassical constant. It's the same idea, right? When gamma is large, you're closer to semiclassics. That's the Eisenman-Lieb argument quantifies this. We have seen the Lieb-Thirring result where they have the semiclassical constant for gamma greater than 3/2 for Lieb-Thirring. And here, this Berezin-Liao and Kröger result, where for this problem we see the semiclassical constant. Okay, that is in favor of this, speaks in favor of this Polya conjecture, and sort of by extension also for this Lieb-Thirring conjecture, where we expect a similar transition towards a semiclassical constant for large gamma. Okay, so that was a review. There are many more things that I could say. This is again a beautiful proof that you will see in the lectures, but I hope I gave you a rough outline about the questions that you care about.